how's it going? So the problem today we have is optimization of binary search trees using dynamic programming. So this is the part one of the 2 videos I'll be posting on this topic, and in the part one we're basically trying to understand what exactly is the problem here, what is binary search tree, and what does optimization of binary search tree mean. Like what exactly are we trying to do here using dynamic programming. And in the second part we'll take a example which will hopefully clear up all the doubts, and hopefully you'll be prepared for your final or midterm or whatever you're preparing for on this topic, and you'll be able to solve the problems similar to those. And the problems, if I can talk about it a little bit right now, is something like you'll be given a bunch of keys and values, and you'll be asked to find out the best or the optimized binary search tree for those keys and values. And we'll discuss as to what exactly does that mean. But first we need to understand what exactly is binary search trees, because I know myself and a lot of people are not from computer science and may not have exposure to this topic. It's pretty straightforward, it's not rocket science, it's super simple. So let's get started with that. Alright, so what is a BST? So let's assume you've been given these keys 1, 2, 3 and some values attached to those keys itself right here, right? Now let's say that I take any one of the keys as a root node, and by root node I mean the first node here. In each tree you can see the first node, that is the root node. And there are some constraints to how a binary search tree is organized for it to be called a binary search tree. Let's say that if I take a root node, let's say that I pick a key as a root node, right? And any one of these 3 keys, then the keys with lesser or not lesser values, make sure you understand this, make sure it's clear to everyone that we're not looking at the values when I say less or high key. I mean just the numerical order of the key itself. So when we pick the root node, the key to the lesser keys to the root node has to go on the left side, and the keys that are higher than the root key has to go on the right side of the root key. And that's basically it. That's the only constraint we have to keep in mind for it to be called a binary search tree. So let's see the examples, and it will be pretty clear as to what's a binary search tree, what's not. Alright, so let's say for this example, we'll first take key number 1 as the root node. So we'll take 1 here. Next key we will take, let's say 2. So 2 is greater than 1, not by value. Please keep in mind, you just don't see the values right now. Values do not concern us at this point of time. We're only concerned about the keys, the numerical order of the keys. So key number 2 is greater than 1, so it goes on the right. Key number 3 is greater than 1, so it should be on the right. On the right there's key number 2 already there, so is 3 greater than or less than 2? It's greater than 2, so it will go on the right of 2 as well, and that's how the tree looks. For the second example, let's say we have the root node same, key 1, 3 is greater than, but the next key we take is 3, so 3 is greater than 1 on the right. 2 is less than 3 but greater than 1, so 2 will end up on the right of 1 but left of 3. So this is how our tree would look, and those are the only 2 configurations we can do with root node as one as a root node, and then we'll switch the root node to key number 2. So 1 goes to the left and 3 goes to the right. That's the only configuration we have for 2 as well. With 3 we have 2 configuration. On the first one we'll take key number 1 first before the second, so it goes on the left of the 3, and 2 goes on the left of the 3 but right of the 1. Similarly, the third one we have 2 on the left of 3 and 1 on the left of 2 and 3 as well. And those are the only 5 configuration we can have with 3 keys. You can take any number like key number 51, 12 and 60, and you'll still end up with only 5 configuration. as you can figure it out on yourself by yourself, but that's how it is. Now another important thing is the levels. So we always call the root node as level 1, and after that just increase the levels. Like this is the second level, this is the third level. You can see the dotted lines I've passed on to all the trees. You can see that this tree, it only has 2 levels, 1 and 2. And but don't jump on the conclusions that that's the optimal tree, since we have lesser number of levels, few levels, as we'll see into all the examples down here, that might not be the case every time. So just don't worry about it right now. All right, let's see. So far so good. You guys got it. Like, these are the 5 binary search trees we have, and remember, all these are correct binary trees. There's no right or wrong here. All this, no one can tell you, oh, this is the wrong one. All these binary search trees are correct, are perfect. You can use any one of them. But the question here that we're trying to solve is, which binary search tree should we use? Which is the optimal? And now the bigger question here is, what is optimal binary search tree? So by optimal, we mean like we want to search which binary search tree has the lowest cost of search, which is the best one in that I should use, that I can search the keys or values I want with the fewest search of cost search. Cost of search. All right, so how do we calculate cost of search? So let's see the examples, and that will clear up everything. So let's take the tree number 1 we had here, 1, 2, and 3. So to find the cost of search of the entire tree, we will add up cost of search of all the levels. So for each level, we find the cost of search by multiplying the level number to the value attached to that key. So now we want to take a look at all the values, right, that were given to you in the problem itself. So let's see. For the first level, we have the value as 20, level is 1, so that gives us 20. Second one, we have key number 2, value attached is 10, and it's on the second level, so multiply by 2. For the third one, we have the value for key number 3 is 60, multiplied by level is 3. And if we sum these 3 up, we get 160. All right, so far so good. Let's move on to the next one. And here you can see the value attached to key number 1 is 20. So 20 multiplied by 1. With key 3 is 60, but the level is 2 now. So 60 multiplied by 2. And for key number 2, we have value 10, but level is 3, so multiply by 3. So we have 20 plus 120 plus 30, that gives us 170. Okay, so that's worse than the first one we had, so we can already just ignore it. We're pretty sure that this is not the optimal tree. This is not the optimal BST. All right, so let's go to the third one. And now here, this is a little bit not tricky, it's pretty simple, but you just want to be careful for the first time because it's not the same as the first 2. This only has 2 levels, so keep that in mind while you're calculating the cost. So you go key number 2, value is 10, level is 1, plus key number 1, value is 20, and level is 2. And key number 3, value is 60, but the level is 2 again. There's no third level here, so that's good. But the total is, well, it's still 170, though. That's not better than what we had before, so you can ignore this one as well. So this is definitely not the optimal binary search tree as well. Similarly, we do the third one, and we find that for the third one, we got the value as 130. Interesting. So this is the best we have so far, because we want the optimal, we want the minimum cost of search. And all right, do we have a contender in tree number 5? Let's see. Is it 3, 2, 1, 60 multiplied by level 1, 10 multiplied by level 2, and 20 multiplied by level 3, which gives us 140. So close, but not the best. So for this particular problem, we finally found out that tree number 4 is the optimal binary search tree. And as I said before, a good observation here is that The fewest number of levels does not mean the optimal BST, as you can see in this case, that this has 170 and this has 130. So this definitely is not the best tree number 3. Tree number 4 is the optimal BST we want to find out. So this is basically the idea behind the problem that we're trying to solve here. Now you might be wondering, so what's the problem? We can just solve it like this. Why do we need an algorithm? Well, that's where you're wrong. We need an algorithm because this is just three keys and just 5 BSTs. So you can just draw these and find out what the answer is. But in the real world, with like large data, as imagine you have like hundreds of keys and they'll be like infinite, well, not infinite, but like a lot of BSTs, and it's not practically possible to do the whole process for every one of them and find out the optimal binary search tree. And that's why we need to learn the algorithm, which we'll do in the part 2. And just a heads up, I'm not gonna go into the algorithm like step by step. You can just refer to the book for that, and by the book I mean the algorithm book Cormen. But what we will do is we'll see the equations and understand, if you're given a problem in your exam, how to solve that and how to finally conclude the binary search tree using the tabular methods and the equations that are used in the algorithm itself. So stay tuned for the next one, and we'll see the example, which should clear up a lot of things. All right, catch you in the next one.